Hello everyone, I'm Yukio Nozaki from Keio University, Japan. First of all, I would like to thank the organizers for inviting me and giving an opportunity to present our recent work. Today, I will be talking about our quantitative study on spin current generation using vorticity in solids, which is produced by such surface acoustic waves. This is a collaborated work with Professor Matsuo of Kaguri Institute of Theoretical Science, China, and Professor Maekawa of Riken, Japan. All of the experiments have been conducted by my student, Mr. Grimune and Mr. Tateno. This work was supported by JST CREST program. This is an outline of my talk. We have three topics for quantitative understanding of spin current generation using a surface acoustic wave. Before getting down to the main topics, I'd like to briefly introduce you the concept of spin current generation via local angular momentum conservation. As you know, a spin current has been widely used to control spintronics devices. However, we need ferromagnets and/or heavy metals with strong SOI for generating spin current so far. Recently, an alternative method without using these materials has been theoretically proposed by Professor Matsuo. The theory is based on the conservation law of local angular momentum between macroscopic rotation and microscopic spin, whose Hamiltonian is similar to conventional SD interaction between macroscopic magnetization and microscopic electron spins. The Hamiltonian promises the conservation among spin angular momentum, macroscopic rotation, and macroscopic magnetization. Similar to the traditional gyromagnetic effect demonstrated by Einstein, Doherty, and Barnett, the effect can be enhanced by increasing the rotating frequency. As shown in this animation, the Rayleigh-type surface acoustic wave comprises elliptical particle motions in the vertical plane parallel to the wave vector, which reaches the gigahertz order vorticity, whose amplitude decays exponentially along the depth direction. The gradient of vorticity leads to a non-uniform spin accumulation via spin vorticity coupling, which generates a temporary and spatially varying spin current as shown in this animation. To demonstrate such a spin current generation using the SAW, we conducted the following experiment. First, we prepared a bilayer consisting of non-magnetic copper and ferromagnetic permalloy on the piezoelectric substrate. When the surface acoustic wave propagates at the bilayer, an AC spin current is generated in copper and it is diffused toward permalloy. Such a spin current periodically gives an alternating spin transfer torque onto the magnetization, and spin wave is subsequently excited at the resonant field. Owing to an energy balance in the bilayer, the excitation of spin wave resonance, whose amplitude is proportional to the square of spin current, leads to a reduction of surface acoustic wave amplitude. This panel shows the first experimental demonstration of the spin current generation in copper film by injecting a surface acoustic wave. As schematically shown here, we prepared a conventional SAW filter comprising a permalloy copper bilayer between transmitter and receiver of the surface acoustic wave. We measured the attenuation of surface acoustic wave using a vector network analyzer as functions of microwave frequency and static external field applied along the wave vector of the SAW. The right figure shows a color plot of reduced microwave absorption with respect to the peak intensity of the surface acoustic wave. The solid curves represent the condition for exciting spin wave, while the dotted line here is the excitation frequency of surface acoustic wave. As you can see, a large microwave absorption appears when the external field is consistent with the resonant field of spin waves at this surface acoustic wave frequency. The result seems to support that an AC spin current is generated in copper via spin vortex coupling of the surface acoustic wave. However, there are still some open questions. First, there is no clear evidence that the gradient of surface acoustic wave vorticity needed for spin current generation exists in copper thin film with a thickness of a few hundred nanometers. Second, to understand the spin vorticity coupling quantitatively, we must evaluate the AC spin current in copper as a function of amplitude of lattice strain. Third, the theory for spin vorticity coupling expects two different sources for spin accumulation. One is the time derivative of local angular momentum omega, and the another is omega itself. We must examine which is the predominant factor. Moreover, there is a renormalization factor in the analytical expression of spin current, which is hard to be determined theoretically. It is significant to quantify this factor because this magnitude determines the conversion efficiency between the local angular momentum of the soul and the spin angular momentum. Now let's move on to the first topic. Here we observed an acoustic spin wave resonance to examine the depth profile of the lattice strain in a symmetric film on a piezoelectric substrate. As shown here, the acoustic spin wave resonance and its non-reciprocal feature have been discovered in nickel films. These features can be fully understood by the magnetoelastic effect. Especially, the non-reciprocity is attributable to the cross-term of the normal and shear strains existing in the power loss formula, this one. It is known that only the shear strain changes its sign when the wave vector of the soul is reversed while keeping the magnetization direction. When the normal and the shear strains coexist as seen in the Rayleigh-type surface acoustic waves, the intensity of power loss is changed with the reversal of wave vector that leads to the non-reciprocity. In our study, we examined the depth profile of strains from the amplitude of this non-reciprocity. The top figure shows the experimental setup for measuring the non-reciprocal spin wave propagation in a nickel film covered with silicon film. The silicon thickness was varied from 10 to 400 nanometer, although the thickness of nickel was fixed at 20 nanometer. The device was designed so that the surface acoustic wave with a frequency of 1.85 GHz was excited. From the boundary conditions for free surface, a largest normal strain appears at the surface where the shear strain becomes zero. Ratio between normal and shear strains therefore depends on the distance from the surface. Consequently, as shown in this figure, the non-reciprocity of spin wave resonance increases with the strain ratio. We can examine the depth profile of the strain ratio by measuring the non-reciprocity as a function of silicon thickness, which varies the depth of this nickel film from the surface. Left and right figure shows the color plots of the reduced microwave absorption and the angle magnitude plane of the static external field measured by S21 and S12 respectively, where the wave vector of the surface acoustic wave is opposed. Here the silicon thickness is fixed at 400 nanometer. As shown here, a strong microwave absorption appears at either polarity of external field, which depends on the wave vector of the surface acoustic wave. Namely, as shown in this animation, highly unidirectional propagation of spin wave appeared clearly. The top left figure shows the field dependence of the reduced microwave absorption at an angle of 30 degrees in the S21 measurement. The right figure plots the non-reciprocity and the spin wave amplitude as a function of silicon thickness. Increasing the silicon thickness enlarges and the asymmetry of the spin wave resonance. The non-reciprocity factor was approximately 10 times larger in the nickel silicon bilayer than the value reported in the nickel single film. By adopting the relation between the non-reciprocity and the strain ratio, this one, expected for semi-infinite silicon, we can expect the depth profile of the strain ratio from this experimental results. The green upside-down triangles are the strain ratio obtained from the finite element method calculated as a function of silicon thickness. As you can see, the estimation of the strain ratio from the non-reciprocity factor is quantitatively validated by the comparison. Finally, we roughly estimate the depth profile of the local angular momentum. From the silicon thickness dependence of the strain ratio, the ratio 1.1 and 3.14 silicon thickness of 200 and 400 nanometer respectively. The right figure shows the relation between the local angular momentum and the strain ratio expected for semi-infinite silicon plate. We confirmed that the local angular momentum was reduced by 17 and 32% at 200 and 400 nanometer from the surface respectively. Namely, our results suggest that the gradient of local angular momentum needed for spin current generation exists even in submicron or deep submicron thick films on piezoelectric substrate. Now let's move on to the second topic of this talk. Here, I will show you the acoustic spin wave resonance in the permalloy film, whose magnetoelastic effect is much weaker than in nickel. The static field was applied parallel to the wave vector of the soul. We confirmed that the strongest microwave absorption was observed at the magnetic field for which the excitation frequency of MSBW mode matches the soul frequency here. Moreover, unlike the spin wave resonance in the nickel, the spin wave resonance is almost less vocal. This suggests successful excitation of magnetostatic backward volume wave via gyromagnetic Barnett effect. A more explicit difference between the Barnett and the magnetoelastic effects is demonstrated by examining the angular dependence of the spin wave resonance amplitude. Magenta guidelines are the spin wave resonant field as a function of field angle. Similar to the previous report, the maximum intensity of spin wave resonance in nickel was non-reciprocal and appeared at 45 degrees, which suggested the coexistence of majority normal strain and minority shear strain in the Rayleigh-type surface acoustic waves. Conversely, the strongest microwave spin wave resonance in Pomeroy was observed at 0 degree. This is evidence that the Barnett field excites spin wave resonance in the Pomeroy because the Barnett field is always collinear with the local angular momentum of surface acoustic waves. Consequently, the magnetic torque owing to the Barnett effect is maximized at this 0 degree. From the intensity of spin wave resonance owing to the Barnett effect, we can estimate the lattice displacement of the surface acoustic wave. This panel schematically shows the power loss diagram in the device. Description for k squared, t, and alpha are shown here. If the spin wave resonance is excited, the value of this alpha, representing the transmission coefficient of microwave in the Pomeroy film, becomes less than 1. From this diagram, it is easily found that the intensity of spin wave resonance is evaluated by the product of the peak intensity and attenuation of the surface acoustic wave, which depends on the volume of Pomeroy, angular frequency, magnetic susceptibility, and Barnett field. Finally, we can estimate the intensity of Barnett field at 1.3 microtesla, which is associated with the lattice displacement of 6.8 picometer for -5 dBm microwave applications. In the previous panel, we have measured the gyromagnetic attenuation of the surface acoustic wave owing to the spin wave excitations by a Barnett effect. It is noted that such a gyromagnetic effect in surface acoustic wave should be reciprocal, as can be inferred from the Einstein-Horst and Barnett effects originally observed in an iron rigid body. Recently, we have succeeded to observe that not only the amplitude but also the velocity of surface acoustic wave are modulated by the Einstein-Horst torque, which comes from the back action of the spin wave excitation. The top and the bottom figure on your right-hand side shows the experimental and the numerical phase shift of surface acoustic wave appeared at the resonant condition for MSBW. As you can see, the Einstein-Horst torque caused by back action of the excitation of MSBW produces a bipolar phase shift, which shows an acceleration and deceleration of surface acoustic wave. Interestingly, we also found that the maximum phase shift can be quantitatively explained when we assume that the amplitude of such Einstein-Horst torque is completely consistent with the magnetic torque caused by the Barnett field. This result suggests that the gyromagnetic conversion of the angular momentum between electron spins and lattice system is ideally adiabatic in a gigahertz frequency regime. In this presentation, we showed the spin wave resonance excitations using acoustic spin current and Barnett effect and magnetoelastic effect. These spin wave resonance can be distinguished from those frequency dependencies of the spin wave amplitude. As shown in this equation, the local angular momentum of a Rayleigh-type surface acoustic wave is proportional to the square of frequency. This animation shows the temporal evolution of local angular momentum omega y, which decays exponentially from the surface, and its gradient is roughly proportional to the frequency. The amplitude of spin current should be proportional not only to the amplitude but also to the gradient of the spin accumulation originated from this capital omega y and capital omega time derivative of capital omega y. Consequently, the spin current is expected to be proportional to cubic and or quartic of frequency. In the case of Barnett field in ferromagnet, its amplitude is simply proportional to capital omega, and thus its amplitude shows second power law with respect to frequency. The magnetoelastic field is proportional to the strain tensor whose intensity is proportional to the frequency. From the power loss formula, we found that the intensity of spin wave resonance caused by the spin transfer torque of AC spin current in copper, Barnett, and the magnetoelastic effect in permalloy shows different frequency dependence as summarized in this table. Namely, from the frequency variation in spin wave resonance intensity, we can identify the predominant factor of the spin wave resonance. This figure shows a double logarithm plot of reduced microwave absorption as a function of reduced surface acoustic wave frequency. And the stars and upside-down triangles represent the data for nickel and permalloy single film. As you can see, both plots are well fitted by linear functions, and the value of gradient gives the order of power law with respect to frequency. The gradient for permalloy suggests the Barnett effect predominantly appeared owing to the negligible magnetorestriction effect. We can also conclude that the in-plane and out-of-plane magnetoelastic fields excite the spin wave resonance in nickel because the gradient is between 2 and 4. In fact, we have observed the non-reciprocity of spin wave resonance in nickel, which also suggested the coexistence of normal and shear strains. In the case of bilayers, we observed much higher power law than the case in nickel and permalloy single films. As shown here, nickel copper and nickel permalloy bilayer shows approximately 1/8 power law with frequency. This means that the spin wave excitation predominantly occurred via spin transfer torque of AC spin current attributable to the spin accumulation owing to local angular momentum capital omega y itself. Interestingly, the AC spin current originated from the spin accumulation owing to the temporal variation in the local angular momentum is invisible. This is attributable to the fact that the electron relaxation frequency is much higher than the Sol frequency. When the poor conductive titanium is combined with permalloy, the order of power law clearly decreased from 1/8 to 1/5. The result quantitatively supports the theory that the spin current generated by a spin vorticity coupling is proportional to the conductivity. Finally, we try to evaluate the parameter which represents the conversion efficiency between local angular momentum of the Sol and the spin angular momentum. We have already succeeded to estimate the amplitude of surface acoustic wave using a Barnett effect. Moreover, from the frequency dependence of the spin wave resonance intensity and the kappa palmaroid barrier, we found that the spin current comprising theta was predominant component. And the third topic, we evaluate the AC spin current using the inverse spin Hall effect in platinum palmaroid kappa trilayer films. The spin wave resonance in palmaroid pumps DC spin current adjacent platinum layer, which leads to a DC Hall voltage owing to the inverse spin Hall effect. From the intensity of Hall voltage, we evaluated the AC spin current, which was necessary for evaluating this theta value. Here, the saw frequency was set at 1.85 GHz. As shown in the top figure, the intensity of microwave absorption was maximized at the magnetic field of 4.87 mTesla, which corresponds to the resonant field at this frequency. Bottom figure is the Hall voltage as a function of magnetic field measured while applying the surface acoustic wave with the frequency of 1.85 GHz. The absolute value of the Hall voltage was maximized in the positive and negative resonant field where the strongest microwave absorption appeared. We also confirmed that the Hall voltage changed its sign when platinum was replaced by tungsten and was eliminated by inserting silicon dioxide between platinum and palmaroid. These results confirm that we can observe the spin pumping effect owing to the MSBVW excitations. Here, we should note that the magnitude of DC spin current is uniform in the whole platinum film, although the dynamic component of the spin wave is periodically modulated in palmaroid. This is because the integral over a period of magnetization precession and the equation for pumped spin current is invariant under the time transition transformation of the integral. Consequently, we can calculate the magnitude of Hall voltage in a manner similar to the conventional spin pumping with a uniform mode excitation. From the microwave absorption owing to the Barnett effect and the inverse spin Hall voltage caused by the spin pumping from the MSBVW, we can evaluate the saw amplitude and the AC spin current produced by the saw respectively. Now finally, we obtained the value of theta as large as 2.6 times 10 to 6, which is 4 orders of magnitude larger than the value expected for liquid mercury flow. Theoretically, the conversion efficiency of angular momentum from lattice into electron spins becomes larger when the difference of energy scales is smaller between the lattice motion and the spins. Indeed, the frequency of local angular momentum of Rayleigh type surface acoustic wave used in our experiment is 6 order of magnitude higher than in the liquid mercury flow. This is a summary of this talk. From the observation of acoustic spin wave resonance in Keio second bilayer and palmaroid single layer, we succeeded to evaluate the gradient of local angular momentum and absolute amplitude of the surface acoustic wave respectively. The frequency dependence of the spin wave resonance intensity suggested that the effect of spin vorticity coupling on collision or relaxation between the spins were a predominant factor in the spin current generation using the surface acoustic wave. From the acoustic spin pumping experiment in platinum palmaroid kappa trilayer, we could determine the conversion parameter of angular momentum from lattice vorticity into electron spins, which is 4 orders of magnitude larger than the liquid mercury flow. For the further understanding of microscopic mechanism of the spin vortex coupling, the material dependence of this theta should be investigated, especially the correlation with the strength of spin-orbit interactions. The detail of all topics are described in these publications. If you have any question or comment for this presentation, please send me an email. This is the mail address. And thank you very much for your kind attention.